Then welcome to the last lecture of the day and also the last lecture from my side in this GIAN course. We will talk about future applications in the end, and we'll have a brief summary and a wrap up of the course so far. We're coming from the lab experiment on active vibration control. Time was a bit short, but I think you got an idea about the vibrations of the beam and how the actuators work on the vibration. And yeah, now we're at future applications. Tomorrow morning is the exam at 10:30, 1 hour. We will say something about this also in this lecture. Then we have some time, Hendrik and I, to do the evaluation, and then we have the grades and concluding remark after lunch. So we will revisit key concepts in this lecture. We'll have a look at a brief recap on the labs as proof of concept. Hendrik will do this, and then I have some future applications brought with me to illustrate what you can also do with smart structures, and then a slide again on the exam. Okay, what makes the structure smart? This was really in the beginning of the lecture. We have a system chain with sensors and actuators picking up signals from disturbances, structural excitation. The sensor signal is then used to generate a control signal with a controller to generate an actuator signal and act again on the structure, for example, to damp vibrations. And what is important is that the sensors and the actuators are made from multifunctional materials and placed really in the loath path, so they are multifunctional, have sensing and actuating functions, and are also load-bearing. Smart structures comprise 4 distinct objectives. So active shape control, we will have a look on that also. Then structural health monitoring, which was no clear focus of this short course. We only briefly introduced it. Active vibration control and active noise cancelling. These two are closely connected together, and all of them target the influence of the elastomechanical properties. What are multifunctional materials again? A functional material is an energy transducer, which, for example, transduces mechanical to electrical energy and the other way around. A multifunctional material, in the sense of our course here of smart structures, is a structural material which also has actuating and sensing properties. Examples of these sensing and actuating materials are piezoceramics, which use electrical fields, shape memory alloys or shape memory polymers, which use a temperature change, or magnetostrictive materials, which use a magnetic field. And for sensing, we want to record or use kinematic and thermal changes and convert them into electrical signals to record them. And for actuating, it's the other way around. We have a control signal amplified and transduced the control signal or the electrical signal into a motion quantity. The conversion is not perfect. We have disturbance factors like losses, so nonlinear behavior, and also not hysteresis effects due to heating, due to domain wall conversions. And we introduce key parameters like the blocking force, the blocking stress, free displacement, free strain, work capacity, and this specific energy, and structural conformity. In our really simple example with the spring model, we have by definition that the stiffnesses agree, so structural stiffness of the surrounding structure equals the stiffness of the actuator, and then the work capacity of the actuator is at a maximum. Then we introduce the work diagram, where we can find also our two key parameters, the free displacement here, which is the maximum unconstrained change in length of a multifunctional material achievable through energy input. Unconstrained, so we have no force applied, therefore we are here on the x-axis. So here is the free displacement, and the second parameter, the blocking force, is defined as the force we require to push back a multifunctional material that has been elongated to its maximum by energy input, so push back to its original length, so we don't have any displacement. We are here on the y-axis at the highest force here, the blocking force, and it's still with an active field, so field activated. And we can also see the structural conformity here in this diagram. This is the line for the actuator, this is the line for the structure. If they have the same slope, meaning the same stiffness, then here the area under this curve is maximum, so maximum work capacity. Then we moved over to the operating principle of piezoelectric transducers. The operating principle is that we have a non-centrosymmetric crystal, so mechanical stresses induce surface charge, which is the direct piezoelectric effect, and the other way around, an electric field induces a strain at approximately constant volume. This is the inverse effect we use for actuation. We can use the piezoelectric effect only after below Curie temperature, because otherwise there's no non-centrosymmetric crystal. And to use it macroscopically, we need a polarization process, because otherwise we have a spontaneous polarization in all 6 possible directions, which would cancel each other out, so we can't use it for sensing or actuating. We do this, or during the polarization process, we have domain wall motion and domain reorientation within the grains, and we align globally the domains, so the dipole direction in the domains, so that we can use it on a macroscopic level, and we keep a remanent macroscopic polarization if we remove the field after polarization. Then we had 2 typical curves, hysteresis and the butterfly curve. First one is a ferroelectric polarization over electrical field loop. We have marked there the remanent polarization and the coercive field strength, and the butterfly curve is the curve which shows the strain over the electrical field. And there we had local minima at the coercive field strength and also a maximum at the maximum field. Advantages and disadvantages of piezoceramic materials are that we can apply high forces. They are comparably stiff. We can also use them good, or they are good usable for dynamic applications, have a high resolution, need low static power, but the behavior is temperature and aging dependent. We can depolarize the piezoceramic if we go above Curie temperature or have mechanical shocks or large electrical field. And we have a pronounced hysteresis and also losses, and we need a high voltage amplifier to drive them. So the direct piezoelectric effect, the effect we use when we use this multifunctional material as a sensor, again is caused by the crystalline structure or the asymmetry in the crystalline structure. The charge center is not the geometric center in the crystal, and if we have an external loading, this would distort the lattice, and this yields to a surface charge which we then can measure. Then we had a lecture on the piezoelectric material behavior. We learned that with the D33 effect, which is a larger effect than the D31 effect, we can achieve free strains up to 0.1%, which is not much. And the free strain of the transverse effect, D31 effect, is approximately only 30% of this 0.1% in a 3-3 direction. We assume that the volume of the ceramic remains constant during actuation. And after polarization, we get an anisotropic behavior electrically as well as mechanically. So also the stiffness of the material after polarization changes. For example, in one direction we have 60 gigapascals, and in the other direction only 40 gigapascals. Our characteristic parameters are specified for small signal behavior. There we neglect the nonlinear transduction and also losses. But in large signal operation, we have an hysteresis of 8 to 15%. And we can say that towards lower temperatures, the active strain decreases by a factor of 0.2% per Kelvin. Having a look again at the inverse piezoelectric effect, and there especially on the hysteresis, so we apply a field if we want to use the material as an actuator. Then we can see here if we apply first a high electric field, then we are going up from this point, from the origin here, and then we remove the field again, coming back to point 1. So we are here now. The area between these two lines is the hysteresis, a measure for the loss. And if we go up to point 3 again, so smaller electric field than before, then also the hysteresis is smaller. And this is the inverse piezoelectric effect because we apply a field and want to use a deformation or elongation. Then we can have a look again at the butterfly hysteresis, especially on the usable operating range. We said that possibly, or it's basically possible to use it between minus EC, the coercive field strength, and up to E max, but in real application we limit it to EC divided by 3 and 50% of E max to be to stay away from depolarization here and a breakdown of the piezoceramic on the other end due to too high fields. And so the technically usable range is marked here in yellow, and for our simple modeling, analytical modeling of the piezoceramic effect, we assumed small signal operation, which was only would be a straight line here in this operating range. Then we had a look at electroactive polymers, different types. First, electroactive, electroactive polymers, piezoelectric polymers like PVDF films. PVDF is the only commercially available material of this material class, which is a semi-crystalline fluoropolymer, and it also has a D3, or it has also piezoelectric behavior, and we use the D31 and the D32 effect, so just the in-plane effect of the film. A different class were the dielectric electroactive polymers, where we use dielectric elastomers and the Maxwell stress, and we can generate very large planar strains at high elastic fields. We had a video where this membrane was expanding. Then we had a look at ionic electroactive polymers, ionomer polymer metal composites, and conjugated polymers, which changed their volume by ion migration in an oxidation and reduction process. And therefore, with this, we could also create bending actuators, for example. Advantages and disadvantages of these materials are that PVDF is flexible, light, has a wide frequency range, but has a low modulus and also low energy density. So it's better to use it as a sensor than as an actuator. And dielectric elastomers can create huge strains and have a high energy density, but we require high fields, and we have a very low stiffness. And ionic electroactive polymers give us large bending at low voltages, which is good compared to the dielectric elastomers, but they are slow, have a low efficiency, and the lifetime is limited, and we have to think of an electrolyte to provide ions for the reduction and oxidation. Then we moved further on to from the piezo ceramic over the semi-finished products to piezo composites and then to functional modules. We start with the powder, which we then form to the green body sinter and do the polarization. The motivation to form these piezo composites is that the ceramic material is very brittle, and we can protect the ceramic with a ductile polymer, introducing these residual stresses, and therefore being able to bear more tensile loads. And with this, we increase fracture toughness and reliability. And it's also good to provide electrical insulation and robust contacting. Then the contacts can stay in place due to the surrounding polymer material. Connectivity, also a topic we visited, was that for these composites we can formulate different connectivity. So 0,3 would be particles in a matrix, 1,3 fibers in a matrix, 2,2 would be stacks of foils, and most of the time we use 1,3, so fiber actuators, which use the D33 effect, or 2,2, like in the stack actuator we had in the lab. For the functional modules, we have the D31 film actuators and the D33 fiber actuators, or the stacks. We had a comparison of the strain voltage ratio. So the D31 can achieve higher strains, but the strain voltage ratio is worse. And I already mentioned the residual stresses due to the encapsulation of the material. So one example actuator, which is quite efficient, is the 1,3 composite, which uses the D33 surface, D33 effect. In this case, round fibers embedded in the polymer combined with interdigital electrodes, which then create a field in this direction, and we also use the effect in this direction. There's another type of these actuators with rectangular fibers, which may have benefits during manufacturing and also contacting by the electrodes. Then we moved on to actuator stroke amplification, defined a stroke amplification factor, which is the free displacement of the system which amplifies the stroke, divided by the free displacement of the piezo monolith. And we reduce, and also the force reduction factor, where we had a look at the blocking force the system is able to achieve compared to the blocking force of the pure piezo monolith. and the product of both serves us as a quality criterion for the efficiency of the stroke amplification. One example are bending actuators, which are based on planar piezo elements, for example D31, using the D31 effect. So we have a field in thickness direction and extended in this direction. And we had a look at trimorphs, comparing them to monomorphs, and could see that trimorphs achieve higher amplification factors and a better or higher quality criterion than monomorphs. And we saw with respect to structural conformity that the substrate properties or the structural properties also matter. The thickness, the Young's modulus of the structure, both affect the performance, and in the case of monomorph actuators, the Young's modulus is beneficial, or a higher Young's modulus is beneficial for these actuators. And we also had a look at alternative concepts like elliptical and rhombic amplifiers, or this Mooney actuator, where a stack actuator with an elongation in this direction yields to an amplified elongation in this direction. Oh, here is an N missing, small typo. One deeper look again at the trimorph, which is a 3-layered composite consisting of 2 active layers with an interlayer, so a carrier structure. Field is oriented in the same direction, but the polarization is oriented in the same direction, but field is in the other direction, or reversed for the both layers. So we have an antiphase actuation, and for this we can bend this upwards and downwards if one layer expands and the other contracts. Then we also had a look at structural integration of smart materials. Materials in fiber form exhibit higher strength, and in some cases also higher stiffness than in compact form. And to use this high mechanical properties of fibers, we create materials which are called fiber reinforced composites, combining fiber and matrix materials. We had a brief introduction on that, and then also a look on how functional modules could be integrated in these fiber reinforced structures. And the partial cutout, like seen here, where we cut some fibers but not all to integrate the composites in the structure, yields the best properties with respect to stiffness and strength. And we also saw that the work capacity of integrated modules is lower compared to applied modules. Then today we started with structure-borne sound and interference. We made a distinction between longitudinal and transversal waves, had also this small experiment for longitudinal waves here in the lecture, and got to know that standing waves form the basis of the solution ansatz with the separation ansatz, where we have the solution for the equation of motion consisting of 2 parts, the spatial and the temporal description. And the vibration behavior of structures can then be described by the sum of their eigenmodes and eigenfrequencies. And we can have by modal transformation each eigenmode described by a single mass oscillator and sum them up to create or to model the overall behavior of the structure. And also eigenmodes act as a filter on the vibration response. So even if we have a broadband signal exciting the structure or disturbing the structure, not all eigenmodes are excited. And then active vibration control, which was the last lecture, or the lecture before. We want to suppress unwanted vibrations. And this could be achieved due to active vibration suppression either local vibration suppression, where we only want to damp one specific point, or a modal vibration suppression, where we damp whole eigen modes, so damp the whole structure or reduce the vibration on the whole structure, but not only on single points. And the number of functional elements required for this modal vibration suppression depends on the number of eigenmodes we want to attend. And we can find the optimal excitation points via the modal index, where the modal strain is highest. Then we had the labs as proof of concept. I think Hendrik will briefly recap what we had in the labs. And in between, I will have, open a video.
So can I continue?
Yeah, sure.
Okay. Okay, so you remember we had 4 labs. We started in the first lab taking or experimentally determining the work diagram. You remember the most important characteristics of the work diagram, which have been the blocking force, the free displacement, stiffness of the actuator, and then the stiffness of the spring, if there is one, so the stiffness of the embedded structure. You may or may not remember that in all labs we have used piezoelectric material only as actuators, never as sensors, so we use the inverse piezoelectric effect. We never use the direct piezoelectric effect. So, bit unfortunate today, we could have used the direct piezoelectric effect. What I didn't show you is that if you do that and you connect now either of those patches, you will immediately see the same thing as the laser distance sensor, because you will see the strain, and the strain will obviously put out the same signal, the same frequencies. So we could have measured the frequencies also without the sensor by only doing like this, and then maybe using one for excitation, one as a sensor, works fine. You will see it on the oscilloscope immediately. So you can use the same setup as a sensor or actuator. That's very possible. Okay, so back to the first lab. Always we use the inverse effect. Here we use this D3 stack actuator. Yes, and then in the second lab we did the butterfly hysteresis. I guess you remember the butterfly hysteresis. And in the lab we determined the butterfly hysteresis experimentally as voltage, or better as elongation in voltage over the voltage, the excitation voltage. And this you can calculate in a displacement, and from the displacement you can determine the strain. So what we had in the lecture was strain over field, and the field you can also get from the excitation voltage by dividing it through the distance between the electrodes. Okay, so this was our second experiment. In the third experiment, we compared different piezoelectric patches, and we had this one very hard to see piezoelectric patch using the D3 effects with piezoelectric fibers oriented like this, and the interdigital electrodes like this, doing a field alternating like this between the single contacts. I guess you remember that. And next to that one, we had a small or thin ply actuator, which is basically exact the same actuator as this, but only a very small slice of this actuator if you slice it in this direction. This is also a D3 actuator. And the last one of those had a D3 actuator, same as we use today in the lab. This is a D3 actuator, where you have two electrodes like this, piezo material in between, polarized like this, but actuation like this. Okay, so actuation not in the same direction as the electric field or as the polarization, and this is why also the effect becomes less, because it basically works with the contraction in the opposite direction. Okay, this was our third experiment, and today was the first day where we used some dynamic testing, and we first of all determined the eigenfrequencies, the first two eigenfrequencies of this beam. By the way, you can calculate them as well. But today we determined them experimentally, and we took the measurement of the displacement here and determined the frequencies. And after that, we did not, but we tried to get the mode shapes by determining the displacement at several points along the length. Okay? So, and what I didn't tell you today is that this setup is not perfect. The mode shape, the frequency, the eigenfrequency is actually a little bit higher, because if I hold it here, what you will see, can you see how the beam shifts? Yeah, so it's not a perfect clamping, because this is not stiff enough, because it's plastic and not steel as it's supposed to be, but then steel was too heavy to bring it. So actually the mode shape would be a bit higher if that would be stiffer. Okay, so small mistake, but nothing which changes the principle of how it works. And if you do it for yourself, then sometimes it makes a lot of sense to put another sensor on the clamping or on the desk even. So we had some experiments on a simplified wing model, where we had a sensor here on the table and the wing here on the table, and everything was massive steel. But anyway, then we got some really terrible noise and we couldn't identify why. And then we had to look at the table, and then it was clear that some vibrations went through the table into the sensor. So what we then did is we used two tables, completely separated, and then the signal got much, much, much better. So you really have to look for the surrounding. Also, the tables in the lab were wood, so we expect that some vibrations, and you realize as soon as somebody steps on the ground, touches the table, everything shifts a little bit. So be careful with your whole setup, that it's as isolated as possible against vibrations. Okay, that was the fourth experiment. Any questions to the labs? Good. I guess if you remember all what we did in the labs and what we did so far, then you're good.
Thank you, Hendrik. So now we're coming to future applications and the outlook. And what I did is I took not from the university, but from the DLR Institute, German Aerospace Center, Institute of Lightweight Systems, where I did my PhD and still have a part-time contract. There's an adaptronics department, and I brought some recent projects they did. You can see here the helicopter rotor blade in the rotor test bench in Braunschweig, but we will not go into detail of this because I had it already on the introduction slides. So first example is the project MorphAir from Morphing Technology and AI Research Group, and the goal was to really show the efficiency of structure or of smart structures in flight test, because there were many subsystem level morphing technology already, subsystem level testing of morphing technologies, but not in flying aircraft or flying structures. So the full aircraft performance was still unknown, and the MorphAir group formed, combining AI-based control and morphing. And they used the scaled unmanned aerial system which was then modified for flight testing. I think the flight testing is not yet done, but the structure is built. They modified the so-called Futura platform and flown it at the Kochstedt Test Center. German Aerospace Center has bought an airport close by Braunschweig to do all the drone testing there, where no public traffic and they called the demonstrator Proteus, which has 2.5 meter span, 30 kilogram maximum takeoff weight, and can reach up to 300 kilometers per hour as maximum speed. And what they investigated was morphing and leading trailing edges, and we are looking in the next slide at the morphing trailing edge. And they also want to have a look at foldable wingtips. And in future concepts, they will also look at variable wing area so that the wing can extend a bit and increase the wing area, as well as winglet positions and aspect ratios of the wings. And I'd like to show you now a video. This is the aircraft, these Proteus aircraft, and here's the wing with the flexible trailing edge. I will go quickly to YouTube, and here you can have a look at the morphing trailing edge of the aircraft. So there are no individual control surfaces, but you can really deform the whole wing, the whole trailing edge, and use them as control surfaces or as high lift devices. So now we are gone to another video. Maybe we leave it by that. So the whole structure or the whole trailing edge can deform. And how was this achieved, this morphing trailing edge concept? Traditional concepts rely on discontinuous skins and sliding mechanisms, but then we have surface gaps and also wear issues, and all surface gaps lead to laminar turbulent transition and increased drag. And in this case, they used a hyperelastic trailing edge concept for morphing, where CFRP skin, here if we look at the cross section, we have FRP fiber reinforced plastic skins, and at the end we have a flexural adhesive connecting the upper and the lower wing cover, so the suction and the pressure side, and then they used conventional actuators like from mechatronics to get forces on the skins, and with that the whole trailing edge could deform. And this smooth gapless contour then supports laminar flow and also reduces drag because we don't have surface gaps anymore. And as you have seen also in the video, we can also have a non-uniform deformation span-wise along the wing. This is the first concept. The second one is a smart cabin lining. In this illustration, I would like to introduce it along this illustration. We have an aircraft with jet engines. The jet engines transmit structure-borne sound to the fuselage. This structure-borne sound is detected with acceleration sensors, and like we saw in the lecture today on active vibration control, we use exciters to generate counter vibrations, and then in addition there were microphones installed in the cabin to pick up the airborne sound, so really the noise the passengers would hear. And the aim is to reduce the structure-borne sound, which then leads to an airborne sound, and improve passenger comfort with these smart ceiling panels. Then all of these sensors, so the sensors and also the exciters, were placed in this ceiling panels here in blue. What was content of the project? One of the research aircrafts from German Aerospace Center was used. This is a Dassault Falcon aircraft, and they did ground tests with the engines running at up to 80% of thrust, and then identified that there are two dominant tones in the cabin at 137.5 Hertz and 404 Hertz. And with this input, they performed simulations on optimum sensor and actuator placement, and also tried to predict the performance. And the results of the design study are shown here. So we have in X and Y direction a plane in the height of the heads of the passengers. So if we look at this picture again, it would be a plane here, and different heights could be measured with the microphones. And then they measured sound pressure level, so the distribution of the sound pressure level at head height and afterwards also on different heights. And this was in the preliminary design study. So these are not measured values, but the calculations for the design. And first row is for 137.5 Hertz, so the first tone. Here without the system, and here with the system, and you can see lowest value of 55. I think it's a dimensionless value, the sound pressure level, but lowest value 55 and highest 80. So most of the area is between 75 and 80, and with the system activated, nearly all of this plane goes down to 55 as a sound pressure level. And in the study also 404 Hertz, so the higher frequency was included. And here you can see already in the simulations that for this it didn't work that well, so there's not much of a difference between the two sound pressure levels measured at head height. And then afterwards, so this is again the outcome of the design study, and then afterwards they again performed experiments, ground test with the system installed in the aircraft, and this is the mean sound pressure value here. It's in decibels, so it's not so sound pressure level in decibels, and measured it at different horizontal planes, 3 to 6. And this bar is the first experiment with the inactive system. Then they activated the system, so sound pressure level goes down for all the horizontal planes except for the last one. And then they performed a second experiment where the sound pressure level in total is less, but the same influence. So for the lower three horizontal planes, they could achieve a reduction in sound pressure level. These are the horizontal planes, so they performed the experiments not only at one height where the heads of the passengers are, but at different heights. And so I was not involved in the project, so they might have also been the horizontal planes 1 and 2, but they included in this plot the horizontal planes 3 to 6 at different heights. So the outcome is that except for the last horizontal plane, it worked well for the other planes. So they could achieve a sound pressure level reduction of 3 decibels in 3 planes, but lower reduction than the experimental predicted one with all the assumption in the design study. And a possible reason for this is changed engine vibration behavior between the initial test to collect the data for the design and then the validation experiments. And maybe some tonal beatings not covered in the design. Then another example, future application, a morphing spoiler for drag reduction. At transonic cruise, shocks can form on the wing, and these shocks cause wave drag and also can trigger buffets, so unwanted vibrations of the wing structure. And the goal was to reduce really this shock strength to achieve a lower drag and also to delay the buffet onset. And they included this shock control bumps here, which could be activated. So if the aircraft is, or the wing is in a state near to these shocks, then they would extend a bit of the surface here to create the shock control bumps and get rid of the shocks. Typical geometry of this local bumps are 0.3 till 0.8% of chord, and streamwise extend up to 10 to 20% of chord. No, streamwise extend, so this is 10 to 20% of chord, and the height is less than 1% of chord. And at least theoretically, this could, for an aircraft with a hybrid laminar flow control wing, reduce the drag of about 2%, which then would, for a typical 9,000 kilometer mission, save 1 ton of fuel. But I think that's only a very rough number and theoretical. How was the design or the morphing element itself designed? They tried to use the existing spoiler. So here a control surface which could extend like this and then stays here to have kind of an air brake. And they replaced the surface of this spoiler with a pre-bended surface, and with this they could use only the spoiler actuator and don't have to introduce another actuator for this shock control bumps. And the idea was to have this pre-bent surface and pull it in a bit so that it has the same geometry as the spoiler, so a smooth surface of the wing again. But if you slightly extend the actuator, it would then get in the pre-bended shape again, and you get this bump. And they investigated also a second concept, two actuator concept with a support actuator, because they found out that it is also necessary to control the position of the highest point of the bump, and therefore there's a support actuator which then has an influence on the pre-bending of this surface, and therefore you can move around the highest point of this shock control bump. So with combining of the material behavior, structural design, and the actuation, in this case you can generate a smart structure for increasing aerodynamic performance. And these were the future application examples I've brought to get you an impression on current research on smart structures. So again, the slide on the exam we had in the beginning. Exam is tomorrow morning at 10:30 a.m. We will have a written exam, 60 minutes. The question focus is on the learning objectives and the key concepts. We try to emphasize on understanding, not memorization, and you need 50% of total points to pass. And if you look carefully again in this presentation, you might find some hints what could be questions in the exam. Okay, and with this I'm nearly at the end, and if you may, I would like to have some oral feedback before you fill in, I think, a feedback form, which is mandatory. You will fill in on Saturday, but I would like to know maybe one of the questions answered. What did you learn about smart structures? Which topics or examples were most valuable? Also, what we could improve in future editions of the course, or any comments on pace, depth, or format. So if you like, I'm happy to get some feedback. Yeah.
Thank you, sir.
Yeah.
On behalf of participants, very nice informative course. As a physics person, I understood that I don't know many things which I learned from your, particularly piezoelectric universal actuator. And thanks, Hendrik sir.
Yeah.
Hendrik sir, for a very engaging lab.
Yeah.
And sometimes teasing lab.
Yeah.
And thanks for all the way coming from Germany to here, all the lab heavy equipment. And what we learned is till now I'm thinking that suppose in flight journey and doing some particularly single engine flight, lot of sound will come.
Yeah.
Is to hear this
The solution at the moment is that the pilot wears a noise cancelling headset, right?
First we keep and remove and again keep. So that time I used to think, is there any way they can decrease this vibration, not from structural point of view, like what you told to keep sensor.
Yeah.
Like now I perfectly come to know that these things are possible and heavy influence is going on. And one thing I observed in earlier where I attended, that in a short courses generally professors will shy to use mathematics because they feel that okay, mathematics means fast you have to go through. Almost I counted 50 new terms are there. She's again asking what is I, what is you, what is lambda, what is what is that.
Yeah.
So you did not shy away from mathematics. That is a good point.
Yeah.
Though we sometimes may feel that okay, little heavy.
Yeah.
But that is what required so that we can go through in future.
Yeah. I try to find a good balance between some mathematics and also some applications.
That is what we did not shy away.
Yeah.
So I hope we maintain that in future also.
Thank you.
That is very important because we tell to students physics is nothing but mathematics only.
Yeah.
Mostly science, mathematics we cannot shy away. That is one thing.
Yeah.
And lab particularly sir tried very best, even though with our unstable tables. Sir.
Yeah.
And I remember him as a digital artist. So thank you, sir.
Yeah. Thank you very much for the feedback. Any other comments? Maybe.
What already exists in this, what kind of sensors and for which effect we can use.
Yeah, and there is much more. We only had a very brief introduction into this. Yeah. Okay, then thank you very much. Also for the nice audience and that you all attended the labs, and then I had the feeling enjoyed the labs, maybe even more than the lecture. Yeah, and
no, there is a perfect correlation. Observe with what you taught and the labs you selected and how he presented. That is perfectly fitted.
That's good to hear. That was the idea, but it may work or may not work. Yeah. Okay.
Because particularly 4 labs are there, then we can see that whatever you taught in the classes, and okay, like that it is the vibrations will control.
Yeah. Maybe in future editions we would save a bit more time for labs, also that we can have the labs not that squeezed. Yeah.
This course was very new to me, and I learned a lot as a new subject. I can see, and thoroughly I have enjoyed and I have understood most of the things what is going on.
Yeah.
Although I am flight dynamics, flight mechanics.
Yeah.
But this is new field for me.
Yeah.
I enjoyed it.
But then the applications are familiar with.
Yeah. What we can add into this course, some
Mm-hmm. 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 Yeah.
Just that.
Yeah.
Rest of the thing, everything was perfect.
Yeah.
Well balanced, practical, and theoretical and equation. Everything was balanced.
Yeah.
Just
Okay.
few numerical problems which we
Then exam also will be difficult.
It may be, yes. Yeah.
Can decrease the percentage.
Yeah.
Pass percentage.
With the numerical problems, right. Okay, then thank you very much. See you tomorrow for the exam, and yeah, have a good